review this lecture and this program? Okay, very good. So just reviewing quickly, because we're going to do it today. So we are with the full theory, the unsteady version of it, so we have to account for the weight, and we have time vary motion. All what we did so far is that we chopped the wings, we divided the wings into n panels. We assigned a vortex to each panel. So the summation of all these vortices will be the bound circulation around the wing. So each one of these vortices is unknown. So this is the steady formulation. To make it unsteady, you have to shed vorticity at each time step whenever there is change in the conditions, angle of attack or whatever. So we place a vortex at the trailing edge. This is one of the things that's not that doesn't see consensus in the community, in the sense that you can locate it at the trailing edge, you can locate it near the trailing edge, and how near, there are some rules for that. We will not go into these details. You can read them in literature. In this class or in this lecture, we will just place it at the trailing edge. So we have n bound vortices, unknowns, and we have one vortex to be shed in the wake that is unknown also. What are the conditions under or at our disposal? Well, for this circulation distribution, we have the no penetration boundary condition at each panel. So these are n equations. So if it's a steady problem, it will be n equations and n unknowns, and that's it. But now, because it's unsteady, we have to shed a vortex. So it's one more unknown. So we need one more equation, and it has to be of different type. As you saw in the theoretical formulations, this extra equation, depending on how you formulate the problem. So for Tudorson, the main governing equation was the Cotta condition. For von Karman and Sears, the main governing equation was the law of zero total circulation. For this formulation, we have no means to apply the Cotta condition actually. If you want to apply the Cotta condition at the sharp edge, right, explicitly, I mean, you need to do it in the cylinder domain and ask that the tangential velocity vanish in the cylinder domain. If you do it like here, so it's much easier to do the law of zero total circulation. So we will do it with the law of zero total circulation, and one of the projects, I guess, Fabian selected. So you will just need to replace the last equation with something else coming from your formulation. So at the end of the day, we have n plus 1 equations. Again, n equations from no penetration boundary condition. And the last equation is the summation of all gammas equals 0. So at any time step, like you see here, so we have here one vortex to shed. In the next time step, this guy has been already determined in the last time step, and now it's in a new location in the wake, and it moves with constant strength. So its gamma is already known from the previous time step. And we have new n plus 1 unknowns. So the last equation will be summation all gammas equals 0. So we'll write it as our unknowns in the left-hand side, and whatever known, we will move it in the right-hand side. So since the gammas in the wake will be always known from the previous time steps, we will move them to the right-hand side, and we'll have here summation all gamma bound equal to negative summation gamma wake. So this is the last equation, and like I said, for the n equations, so we have n plus 1. The last equation is summation of gamma equals 0. The first n equations is the induced velocity, is the velocity normal to the panel is equal to that of the motion. The velocity normal to the panel, the velocity at each panel, come from all bound vortices, all wake vortices, and the airfoil motion. So the one coming from all bound vortices and all wake vortices, so we created this function, Maslach function, Biot-Savart, is just take a point and a vortex location, the point location and the vortex location, and gives you what? The effect of this vortex on that point, assuming unit strength. So if it's not unit, just multiply the result by the value of gamma vortex if you know it, okay? So it's a very easy function. We already did that last time. When we get the whatever from the bios of R, it gives you two components. The x and y components of the induced velocity. If you want to get the normal component, you need to dot it with the normal of the panel. And some all over vortices, so we have some all over the bound, which are unknown, and some all over the weight, which are known. So again, we will move it to the right-hand side. So at the end of the day, this was our main system that will be solved at each time step. A times gammas equal right-hand side. The A matrix, the first n rows of the A matrix is the first n equations, which is the no penetration boundary condition. Okay. The last one is summation all gammas, so 1 times all gammas equal negative summation gamma wake. So we started doing this. At each time step we will solve here, get the gammas. After you get the gammas, then you're done. If you want to get the pressure distribution, here is the equation, the Unsteady Bernoulli. So the distribution of gamma is simply your gamma of this panel divided by the panel width, d. And this guy is d by dt, or partial t. We will do it like any numerical technique, that the simplest thing, which is forward difference. So whatever I have now minus whatever the last time divided by delta t. And what is the quantity that I need to do that? It's this integral. So it's the summation of all gammas up to your x, up to your panel. The summation of all gammas up to my panel I. And we said this was the flow chart. We discussed it last time. Let's go and implement. So this was the bio-Savart function.
Professor?
Yes, please.
How do you calculate the position of the vortices in the wake?
Yeah, we'll position of vortices in the wake, you said?
Yeah.
Yeah, we'll do it.
Okay.
So we did not do this last time. So we just created bio-Savart. Anyone has a problem with the bio-Savart function? Please, if you have a problem, just stop me. Okay, and this is the program that we did last time. We started. So we said this is the input section, your omega of oscillation of the wing, forward speed, chord length or half chord length, the alpha note, mean angle of attack, and the amplitude of plunge. So here I'm doing plunging only, and the pitch location. The time final, or the time of simulation, we chose 2 cycles. So this is 1 cycle. Then here is initialization. We need to choose number of time steps. So actually, this will need some study, right? Need mesh study. So we will do it for maybe 40 or 30 or 20, but then you take, formally speaking, you will have to take this code and make a conversion study, right? To run it for n equal 20, 30, 40, 50, and see when adding more ends, more panels, does not enhance much your solution, so you stop, okay? We actually did that and we found that 40 is not bad, so you might need to do it again. But anyway, for general code, you have to do mesh study here. The same for delta t. So delta t, I told you that this rule is like a rule of thumb. Once you determined your panel width, it's just divided by u infinity, but again, maybe for different applications it would be different. So here you need again the same thing. You need mesh study. So this is a spatial mesh, and here is your temporal mesh, right? We're doing discretization in space and time. Okay, and then some initialization. We will need them because the gamma bound zeros, x, y weight is empty because we don't have any weight points, right? We're gonna add to it each time step. We will add one more wake element, gamma wake and x, y wake. The number of wake elements 0, and each time step we will add to it, right? And then we go to the geometry. So we defined our x bound and y bound is 0 because it's a flat plate. So I'll write here for you. Here you can put your Kimber equation, right? If you have a Kimber equation, it's not 0 anymore, the y. Just put whatever equation is a function of this x, right? So if you have yc as a function of x, you put it here as a function of this x, right? And the same for the xy control we already discussed why we chose the quarter chord of each panel and the 3/4 chord of each panel. If you have a question, please stop me. So here goes the camber equation. We're doing this offline before the time simulation. If it's a rigid camber, but if it's a flexible camber, I would recommend to do a rigid one, and then inside just update it. So all what you need to update is the y location will be this y plus whatever coming from flexibility. One of two things: either it's imposed flexible motion, you're assuming it, you have actuators to do that for you. In this case, it's known motion, so you just add it like here. But if it's just natural flexibility coming from structural model, so you have to solve the structural model simultaneously. So your time simulation will call the structural model and will do the aerodynamic model. At the beginning, you initialize it with the rigid case, but then as you move forward, you call your structural model, get the new deflections, and update it as you go. Okay. Here we already wrote this from last time. This is the dy/dc for your camber. Oh, it's good that they use this. This is the NP at each panel, right? The normal to the panel. Okay, so in our case it will be just 0 and 1 because it's a flat plate. And this is the last point of the trailing edge. Now the influence coefficient matrix, our A matrix. If all the x's, x bound and x control point, they are fixed. Remember, we're doing it in the axes of the plate, axes of the chord. Okay. So with respect to the axes of the chord, in these axes, this is my x and this is my y. So if you have a fixed camber, that's fine. You can have a fixed camber. Relative to this axis, if your x's and y's of the points on the plate or on the panel, if they are fixed with respect to each other, i.e. rigid, right? This is the definition of rigid. A rigid body means that the distance doesn't change as it moves, the distance between points. So if it's rigid, then these x's and y's are fixed in that frame, so you can compute your A outside. And here's what we did. So the first n rows were just the bisevar, right? The induced velocity. This dot product, you can actually replace it by a dot. You can also use the command dot between the normal to the panel, this guy, and whatever comes from bisevar to get the normal velocity. The last row is just ones, as you saw last time. Then here is your imposed motion. We're doing here pitch plunge, but you can do maybe the homework problem, which is this funky motion angle of attack is a function of time. We don't care, put whatever. So this is the power of this method, is that I can use whatever shapes, I can use whatever form with time. It's very convenient for simulation. So we chose, or we assume that this is the desired motion, or this is the imposed motion. Alpha is sine, so alpha dot is cosine, this should be positive, right? And the same for h. H is sine, but h is irrelative. H dot is cosine, we did that. And then this is the motion. Let's get this and put it inside the time simulation. So this is our kinematics, or motion of the airfoil. Okay, we're done with initialization. We have geometry, we have influence coefficient matrix, we have kinematics, whatever. You might want to check before doing anything. So let me just even do this. Let's check our mesh. So let's plot, say, we have a plate, right? So so the x is between 0 and 1, right? And the y is zeros. This is my plate in black. And then I will plot our points. Okay, the xy bound of anything and 1. This is the first coordinate. I'll plot this guy with the xy bound, the y coordinates, which is zeros, and I will do this maybe in red. Okay. Let's see if we have any problem. So these are your discretization, okay? So just to see it clearly, let's have two. And let's also plot the control points to see if everything is going okay or not. Control point. Now we'll do it maybe in blue. Start. So this is your plate. We chopped it into two panels. For each panel we have the quarter core, the control, a bound vortex, and the 3/4 of this panel have control point. So the meshing seems to be okay. Okay? Any question about that? Okay. Inference coefficient, your alphas and stuff. Let's go here. So the time simulation, what is the heart of the time simulation? What's the thing that we really have to do, must do every time step?
Update like the wake vortex thing, like add it up.
Yeah, no, this is to make things work. What's the heart of it? What's the essential equation that you solve each time step? What do you do each time? So for simulation, why do I want to do time simulation? Come on. What do you do at each time step? We solve a linear system. The A gamma equals right hand side, right? This is our heart of this is basically the code. Anything else is just to make this work. The whatever we have here is just to construct the A matrix. And this kinematics is the motion is to construct the right hand side. Everything is just try to prepare this linear system. A gamma equals the right hand side to get the gammas over the airfoil. Because if I have the gammas, then I solve my problem and I can do whatever. I can get the loads, I can get the velocity at any point if I want. Okay, so I want to solve the linear. So this is the first thing in the time simulation, or the heart of the time simulation. To solve the linear system, we need the left hand side and right hand side. So the left hand side is already done, right? Because it's rigid. And if it's not, so you need to update it here, right? So let's get the right hand side. What was the right hand side? The right hand side has how many main components? The right hand side. Anybody remembers? Yeah, I mean, how many main, contributions? Two. Very good. One due to the motion of the